Transformations. Our objectives are that we will graph functions using vertical and horizontal shifts, graph functions using reflections about the x-axis and the y-axis, determine whether a function is even, odd, or neither from its graph, graph functions using compressions and stretches, and combine transformations. Transformation. A transformation is a small, uniform change to a relation. Here is an example of one of the most simple transformations. Let's graph these functions and fill out the t-tables given. So the first function here, f of x, is the square root of x. Let's go to the t-table. The t-table starts with x being 0. The square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. And the square root of 9 is 3. Let's graph those points. 0, 0, 1, 1, 4, 2, and 9, 3. When we connect those points, we can see the shape of the graph, one of our parent functions, the square root graph. Let's look at g of x. For g of x, I have the square root of x and then plus 3. So I'm going to take the square root of 0, which is 0, and then add 3. So I get 3. Square root of 1, which is 1, add 3, I have 4. Square root of 4 is 2 plus 3 is 5. Square root of 9 is 3 plus 3 is 6. You can see that all of the f of x values in the first table, we simply added 3 to those values to get our g of x. 0, 3, 1, 4, 4, 5, and 9, 6. You can see here the graph of this function, and it is the same as the f of x function, just moved up 3 points. So the difference is that every y is 3 units higher than the graph that came before it. Here is another simple transformation. Graph the function g of x, filling out the t-table given. We've started out with the parent function that we had before. With this new function over here, you can see we're not starting out with an x value of 0. If we want to have the same outcome as we had before, we would have to start with a 2, because 2 minus 2 is 0, and then the square root of 0 is 0. So there's an adjustment here in the x's to be able to get the correct output that we had before. Again, we're not going to start with 1 on this point. We're going to use 3. It's 2, the x is 2 more than what it was before in order for us to have the same output as we had before. 3 minus 2 is 1. The square root of 1 is 1. 6. 6 minus 2 is 4. Square root of 4 is 2. And 11. 11 right here minus 2 is 9, and the square root of 9 is 3. So I here have 2, 0, 3, 1, 6, 2, and 11, 3. Okay, so the difference or similarity that we have here is that we had to add 2 to the x in order to get the same output that we had before. When we have to add 2 to the inputs to get the same output. That means that we have shifted right to. Okay. Now in the equation, it looks like we're going to have to subtract 2 from the x. But remember, this formula says that g of x is the square root of whatever input we have minus 2. So we have to put 2 in there in order to get the same output as we had in the table over here. So every x has been shifted to the right 2. You can see 0, we've added 2 to get 2. 1, we've added 2 to get 3. 4, we added 2 to get 6. 9, we added 2 to get 11. And that way we have the same output there. And I am trying to make it where I am taking the square root of perfect squares so you can graph these easily. The transformations we just studied are called shifts or translations. When we have a vertical shift in a function, we have the same function that we had before, f of x, and the new function g of x is what we had before plus k. In other words, k is being added on to the end of the entire function in order to get this vertical shift. We're literally saying that y is k more than what we had before. So if the y is k more than what we had before, then it's going to move it in a vertical way. Now if that k value, if the k value is positive, then the graph is going to shift up. If k is negative, then the graph will shift down. And you'll see this y equals f of x minus 2 type of an equation if we wanted to shift something down 2 units. Now for a horizontal shift, if we start with this function f of x, the new function g of x will be f of x minus h, where h is a constant. And this is a horizontal shift. If you notice the difference between this type of function and this type of function is that the h is grouped. It's grouped with x in that grouping symbol. And again, if h is positive, this graph is going to shift to the right. And if h is negative, the graph is going to shift left, just like the example we just went through. Again, note that grouping with that x is essential if we want to affect the graph in an x way. Let's say f of x is some function 3 times the absolute value of x, and this function's already undergone a particular transformation we're going to learn about soon. But we take the function that we have now and we want to modify the function. Say we want to shift the function left 4 units. Now remember, if we're moving something left, that's going to be in an x direction, and if we want to affect the graph in an x direction, we have to make sure that we are grouping that 4 with the x inside the grouping symbol. And in this place we have absolute value is our grouping symbol. So if we wanted to make our new g of x function, still going to have the 3 out front. The only thing that is changing is that we are going to add 4, to the x inside the grouping symbol of absolute values. Remember, this is so that we can get the same output in that place where that function has moved as we had before. Just think about what x would you put in here to get back to this being 0. It would be a -4 that you would have to put in there, and -4 is going to mean left 4 units for us. -4 inside the absolute values for the x is going to give us 0. Absolute value of 0 is 0 times 3 is 0. Whereas up here, our 0 was just 0. We just use an x value of 0 to get an output of 0 in this function. Okay, on this one, let's say that we wanted to take the f of x function and we wanted to shift it down 1 unit. Well, g of x is going to be the f of x function. It's going to have the same y's. Remember, we're moving this in a y direction. It's going to have the same y's as it did before, but 1 less. In other words, g of x is equal to 3 times the absolute value of x minus 1. Let's complete the following and sketch a graph for this example. Here our graph of h of x is going to be the square root of x plus 1 plus 3. What is the parent graph of this function? When I look at this, I see transformations, a couple of them going on at the same time, but the parent graph with all those transformations stripped away is simply f of x equals the square root of x. So if I want to graph that, we know from before that we had 0, 0, 1, 1, 4, 2, 9, 3. That gave us our square root graph. Make sure and put the arrow at the end there to show that it continues in that direction. Now, what we've done is taken the x and y values here, and when we undergo this transformation here, we are adding 1 to the x in the formula. So for us to get the graph for h of x over here, we're going to need to subtract 1 from the x's in order to get the same output from the square root as we had before, and then add 3 to all of the y's. So 0, I'm going to subtract 1, gives me a -1. 1, I'm going to subtract 1, and that's going to give me 0. 4, I'm going to subtract 1, that gives me a 3. 9, I'm going to subtract 1, and that gives me an 8. And the outputs that we'll have from that are the outputs that we had before plus 3. So 0 plus 3 is 3. 1 plus 3 is 4. 2 plus 3 is 5. 3 plus 3 is 6. Okay, let's see if we can graph this. I have a -1, 3, a 0, 4. I have a 3, 5, and an 8, 6. There we can see we've gotten the same graph that we had before, just that it has shifted to the left 1 unit and up 3. And you can literally just move each of those points if you would rather look at it that way. You can pick this point up, move it left 1 and up 3, and that gives you this point. Take this point, move it to the left 1 and up 3, that gives you this point, and so on. Okay, so you can see how to do it as a graph and also by manipulating the numbers in the table based on your formula. Now let's introduce vertical stretches and compressions. We'll complete the t-tables here and graph each of the functions. This is a well-known function, the quadratic parabola. So we're going to just look at the graph that we have gotten before with this type of function. And the table, you can see -3 put into this. -3 times -3 is a +9. -2 times -2 is +4, and so on. And so we see this symmetry going on in the table, and we see symmetry in the graph. Okay, and let's see what happens to the t-table as we modify the function a little bit. Here I have g of x down here. G of x equals 2x squared, and I'm looking at that. I have the same thing as I had before when I put -3 in. I get a 9, but then I have to take that output and double it, so I get 18. Put in a -2, I get the same thing as I had before, the 4, but then I have to multiply by the 2 that's out front. So every output is getting multiplied by 2 from what we had before. And let's go ahead and graph that. I'm graphing this in red so we can easily compare. By putting a -3 in, I am going to be up here at 18. A -2, I'll be at 8. A -1, I'll be at 2. 0, 0, 1, 2, 2, 8, and 3, 18. And we can connect our dots here smoothly as we can and see what kind of a graph we're getting from the inputs, the same inputs that we had put in before. And then my h of x graph, very similar to what we had with the f of x function, except there's a 1/2 in front. So that means that after we have put in the inputs, we'll have to multiply that by 1/2. So just as before, put in the -3, I'm going to get out a 9, but then half times 9 is going to be 9/2, or 4.5. If I put in a -2, I'll get a 4 out, but then I take that times half and I get 2. If I put in a -1, I'll get a 1 out, but then I take that times a half, I get a half. Put in a 0, 0 squared is 0, times a half is 0, and then 1, I get 1/2, 2, 2, and 3, 9/2, or 4.5. So let's graph those. -3, 4.5, -2, 2, -1, 1/2, 0, 0, 1, 1/2, 2, 2, 3, 4.5. And we'll connect try and make as smooth of a graph as we can. And we're kind of wondering what it is that happened with the functions. It appears that for the same x values, in other words, the same width of points that we put into these graphs, we have stretched or compressed. For the red graph, we are growing twice as fast. In other words, g of x, let me put this in the right color, g of x is equal to twice the y that we had before. And if I'm looking at h of x, we're half as tall as we used to be. So these y's are half of the y's that we had before. So it shortens the graph, it compresses it. And the red is stretching or doubling the height. Given a function f of x, a new function g of x equals a times f of x, where a is a constant, is a vertical stretch or vertical compression of the function f of x. If a is greater than 1, then the graph will be stretched vertically by a factor of a. If a is between 0 and 1, then the graph will be compressed vertically by a factor of a. If a is less than 0, then there will be a combination of a vertical stretch or compression with a vertical reflection. Now a discussion on horizontal stretches and compressions. Let's complete the t-tables and graph this. We have here let's take a look at horizontal stretches and compressions now. I want to complete the t-table and graph for the red g of x function and the green h of x function here. I'll copy down the t-table from what we had in the previous example for our quadratic function. Let's look at the g of x function. Now, if I want to be able to get the same outputs here as I had in this table, I can't put the same inputs. If I put a -3 right here, this would make this a -6, and then -6 squared is 36, and that's not what we want at all. So I have taken my x values that I had before, and I have taken half of those values. So half of -3 is -3 halves, because when I put that in here, -3 halves times 2 is going to be -3, and -3 squared is 9. Same with the -2, I've taken half of it, and so it's -1. If I put that in here, -1 times 2 is -2, squared is 4. Half of -1 is -half. Again, putting that in for x. -half times 2 is -1. -1 squared is 1. Half of 0 is 0. So 2 times 0 is 0. 0 squared is 0. And I'm going to have symmetry help me to fill out the rest of that table. Okay. So what is the effect on this graph? Well, if I have a -3 halves, it's a -1.5, and up to 9, looks like I'm sitting about right there, and -1, 4, -half, 1, 0, 0, 1/2, 1, 1, 4, and 1.5, 9. So what this has done is it has compressed the graph horizontally. So in a left-right way. You notice the 2 is grouped with the x in parentheses, so it affects it in an x way, and in the inverse way that we think it would affect it. Instead of doubling the width, it's halving the width. It's halving the width, so it's compressing it horizontally. Let's try this with the green h of x function. Looking at that, I've had to double all of my inputs from what I had before. Double -3 is -6, because when I put that in for x here, -6 times a half is -3, and then -3 squared is 9. So in a similar fashion, I have to modify what x value I'm putting in order to get the same outputs. All right, so I'm going to have the same y's as I had before. And graphing this, I'll have a -6, 9, -4, 4, a -2, 1, 0, 0, 2, 1, 4, 4, and 6, 9. Okay, and we connect those and try to make it as smooth as you can. And you can see here that you get the same outputs, the same height of all your points for different inputs, and those inputs had to be twice. They had to be, the input, the x's had to be twice what they were before in order to get the same outputs. So you had to double the width. So this is a horizontal stretch. Again, it's grouped with the x. The 1/2 is grouped with the x, and so you know it's affecting it in an x way, and it's affecting it in an inverse fashion from what we would think it would do. Instead of halving the width, it is actually doubling the width. Given a function f of x, a new function g of x equals f of b times x, where b is a constant, is a horizontal stretch or horizontal compression of the function f of x. If b is greater than 1, then the graph will be compressed horizontally by a factor of 1 over b. If b is between 0 and 1, then the graph will be stretched horizontally by a factor of 1 over b. If b is less than 0, then there will be a combination of a horizontal stretch or compression with a horizontal reflection. Reflections. Complete the t-tables and graph below. I have the parent graph, the blue graph, already tabled out and graphed for you. It's one of our well-known parent graphs. Let's look at the red g of x function. G of x equals negative of square root x. And how is that going to look when we graph it? Well, let's put our inputs there. Square root of 0 is 0 times the negative out front, we get a 0. The square root of 1 is 1, and multiplied by the negative out front, I get -1. With 4, the square root of 4 is 2 times the negative 1 is -2. And the square root of 9 is 3 times the -1 in front gives me a -3. Let's go ahead and graph that. I have 0, 0, 1, -1, 4, -2, and 9, -3. Try and connect that smoothly, and you can see there is a reflection. If we would fold our paper along the x-axis, the blue and red graphs would lie on each other, and that's a reflection over the x-axis. When we have g of x equals negative of the square root of x, we're really saying that the g of x, the y's for this, are equal to the opposite of the y's for the other graph, the opposite of the f of x. So it's, you can see the sign of the y values changed. Now, looking at the green h of x function, it's a little different story here. I have h of x equals the square root of negative x. Now, my inputs have changed here. You can see I wouldn't be able to put in square root of negative and then put in a value like 4, because I'd be taking the square root of negative 4. So I have to modify my inputs to get this to work correctly. If I put in a 0, there's no problem there. I've got a negative 0 is 0, and square root of 0 is 0. Now, if I put in a negative 1 here, I have the opposite of negative 1, which is 1, and the square root of 1 is 1. Negative 4, if I take the opposite of negative 4, that is 4, and the square root of 4 is 2. Putting in a negative 9, the opposite of negative 9 is positive 9, and the square root of 9 is 3. Let's see where that lands us. I have a 0, 0. I have a negative 1, 1. I have a negative 4, 2, and a negative 9, 3. And when we connect that, you can see that this is a reflection over the y-axis. In other words, all the x's that used to be positive here, well, they're now negative x's. The y's haven't changed. The y's, we end up with the same value as we did in the blue graph. So it's a reflection across the y-axis. Remember, when you're grouping any kind of transformation in the grouping symbol, here's our grouping symbol here is the square root. When we're grouping that transformation with the x, it's going to affect the graph in an x type of way. And in this case, it's a reflection. Multiplying by a negative is going to be some kind of reflection. If it's negative of the entire function, then it's going to be the opposite of the y's, and it reflects over the x-axis. If it's a negative of the x, again, it's another reflection, but it's a reflection over the y-axis. All right, given a function f of x, a new function g of x equaling negative of f of x is a vertical reflection of the function f of x, sometimes called a reflection about or over the x-axis. If we have the function f of x and come up with this new function g of x equals f of negative x, this will be a horizontal reflection of the function f of x. Sometimes this is called a reflection about or over the y-axis. Complete the table below given that g of x equals f of negative x. So remember here we had to modify the x's in order to get the proper kind of output from the function. So what happens here is that we end up with the opposite of the x values that we had before, and the y values will be the same. And in this way, it is a reflection over that y-axis there. I have here the graph of f of x equals x squared, and I want to graph onto that the function g of x equals negative x in parentheses squared. So let's fill out the table. If I would put an input of -3 here, it would make this the opposite of -3, which is +3, squared is 9. And similarly with 2, the -2 times a -1 in front would make it a 2. 2 squared is 4. The opposite of -1 is 1. Squared is 1. 0 squared is 0. Negative of 1 is -1. Squared is +1. The opposite of 2 is -2. Squared is 4. The opposite of 3 is -3. Squared is 9. So we plot these points and we notice that the new graph lies perfectly on the old graph that we had. And so there was a reflection based on what we know about the reflection transformations, since the negative is in front of
here's
the
an interesting
X
twist on reflection.
inside of the grouping symbol here, then there's a reflection about the y-axis. And so what we notice is that there is symmetry to the y-axis. Just flip it over on the y-axis, like the y-axis is a stick going through that graph. You can flip it and it looks exactly the same once you've made that reflection. I have a similar example here. My f of x function here is the x cubed function. I'll run through that real quick. -2 cubed is going to give us -8. -1 cubed gives us -1. 0 cubed is 0, and so on. So what happens when I put the x's, the same values of x, into the function, if there's a negative grouped with the x inside the parentheses in my transformation function. Well, if I put a -2 in for the x, I get a +2 after, or take the opposite of it. And so a +2 cubed is 8. If I put in a -1, it makes it a +1 cubed is 1. A 0, we'd still have 0. Putting in a 1 would make it the opposite of 1, or -1 cubed, which is -1. Putting in a 2, I would get -2 cubed is -8. Now see what happens when we graph this. I would have -2, 8, and I have -1, 1, a 0, 0, 1, -1, a 2, -8. And we try and smoothly graph this. Okay. We have a reflection again about the y-axis. This time the blue and red graph do not lie on each other if we would graph both of them. We had the transformation last time. They were exactly the same graph, but we can definitely see a difference in the graph here. So there's a different kind of symmetry that is going on with these graphs, and that's what we'll talk about next. The last two graphs show the properties of even and odd functions. And that's defined here. Even and odd functions, a function f is an even function if f of -x equals f of +x for all x in the domain of f. In other words, its graph is going to be symmetric with respect to the y-axis. And we can see that with that first example. And a function f is odd. It's an odd function if f of negative x equals the opposite of f of x for all x in the domain of f. Its graph is going to be symmetric with respect to the origin. In other words, we can spin the graph 180 degrees on the origin, and it's going to sit on the graph will sit back on itself perfectly. So here let's determine if the following functions f through I are even, odd, or neither. So the test is to see what happens when we put in the negative x instead of x. So f of negative x is going to be negative x to the fifth minus 2 times negative x cubed. And this is negative x to the fifth plus 2x cubed. And we can see that this is negative of x to the fifth minus 2x cubed, or in other words, this is the opposite of f of x. So based on our definition, f of negative x is equal to the negative of f of x. This means that this function will be odd. All right, let's try with g of x. G of negative x is equal to 0.75 times negative x squared plus the absolute value of negative x plus 4. When we simplify, this is equal to 0.75x squared plus the absolute value of negative x is going to be the same as the absolute value of positive x plus, and here we came out with the exact same function that we started with. So when g of negative x is equal to g of positive x, this means we have an even function. Continuing here with h of x, let's determine if this is even, odd, or neither. I'm going to take h of negative x. This is negative x to the fourth minus 5 times negative x plus 8. Now negative x to the fourth, because this is an even power, will be the same as positive x to the fourth. Here I have negative 5 times negative x makes a positive 5x, and then plus 8. Now this is not the same as h of x, but it's also not the opposite of h of x either. So this is neither even nor odd. This is neither. Let's try with I of x here. I of negative x would be 3 over negative x, and another way to simplify that would be pull that negative 1 out front. So this is negative 3 over x, which is the opposite of I of x. So according to our definition, I of negative x is equal to negative I of x. We've shown that this function is odd. Symmetry with respect to an axis. So we've seen symmetry with functions, but it actually applies to relations as well, relations that may not be a function. The graph of an equation is symmetric with respect to the y-axis if the replacement of x with negative x results in an equivalent equation. The graph of an equation is symmetric with respect to the x-axis if the replacement of y with negative y results in an equivalent equation. Now, if something is symmetric to the x-axis in this way, some kind of a graph that appears this way, then this will not be a function, but we can still have symmetry with a relation. Symmetry with respect to the origin. The graph of an equation is symmetric with respect to the origin if the replacement of both x with negative x and y with negative y at the same time results in an equivalent equation. Note that the relation is symmetric to the x-axis and the y-axis, and it's automatically symmetric to the origin. So if you've tested for symmetry to the x and y-axis, they both check out. You don't have to check with the symmetry to the origin test. Now, it is possible to have symmetry to the origin yet not be symmetric to the x-axis or the y-axis, such as in the x cubed function that we just saw. In these examples, without graphing, we want to determine symmetry to the axes or the origin. So let's see if we can find symmetry to the y-axis. Do we have y-axis symmetry? To test that, we are going to replace the x with negative x and see if we can get an equivalent equation. Now, negative x squared is the same as x squared, and I'm still subtracting that, and it looks like we have an equivalent equation. So we do have y-axis symmetry. What about the x-axis? I'm going to replace the y with a negative y and see if I can come up with an equivalent equation. And negative y squared is going to be the same as positive y squared. So yes, we have symmetry to the x-axis. And automatically, we have symmetry to the origin because we have a yes here and a yes here. Let's try the next. Y equals x cubed minus x. Do we have symmetry to the y-axis? So to test that, we're going to replace x with negative x throughout the equation. We have y equals negative x cubed plus x. And that is not equivalent, so we do not have y-axis symmetry. Let's see if we have x-axis symmetry. So we replace the y with a negative y and see if we can get an equivalent equation. Let's say I multiply both sides through by negative 1. That would fix my y to be a positive y, but then we mess up the rest of the equation. We're not getting an equivalent equation this way either. So we do not have x-axis symmetry. Now, we tested no x-axis symmetry, no y-axis symmetry, but we still need to test for the origin. Remember, if the x-axis and y-axis both test out to be symmetric, then it's automatically for the origin, but we can still have origin symmetry even if we had no x-axis and no y-axis symmetry. So let's try this. I'm going to put in a negative y for my y. I'm going to put in a negative x for my x. We're doing those at the same time. And so I have a negative y equals negative x cubed plus x. This means y equals x cubed minus x. If I multiply both sides by negative 1 to solve for positive y, lo and behold, I have the same equation that I started with. So we do have origin symmetry here. Let's try this one, y equals x plus 15. Let's test for x-axis symmetry. So y is negative x plus 15. Easy to see. We're not going to be able to manipulate this in any way to get y-axis symmetry. How about x-axis symmetry? So let's try, we've got a y gets replaced with negative y. And if I try and manipulate this in a way to get it solved for just a plain y, I don't have an equivalent equation. So this is a no. Let's try for origin, because we know we could still possibly have symmetry to the origin. So I replace y with negative y. I replace x with negative x. And I see if I can manipulate this in a way to get the same equation out. I'm going to multiply both sides by negative 1. This gives me y equals x minus 15, and that's not working either. So we have quite a variety of cases here with showing all three tests for symmetry. Symmetry to x-axis, symmetry to y-axis, and symmetry to the origin. Some mixed practice here. Let's write a formula for new functions g and h whose graph is similar to f of x but satisfies the given conditions. When we're finished, don't simplify your formula. We start out with f of x equals square root of x, one of our parent functions. G of x is shifted right 4 units, then reflected about the y-axis. So we start this out. Let's do step by step. G of x is going to be shifted right 4 units. So this will be an x minus 4. And then we're reflecting this about the y-axis. So our next step would be to go ahead and replace the x with negative x. So just step by step, apply those transformations. Now let's say that we started with the f of x function and we want to get this h of x function. This h of x function is reflected about the y-axis, then shifted right 4 units. So again, step by step, it's reflected about the y-axis, so I'll have the square root of negative x. And then we want to shift this right 4 units. So in applying that transformation, we'll have the square root of negative. I'm replacing the x with an x minus 4 to shift it right 4 units. Now if we did simplify this a bit, just to see, we have a negative x plus 4 inside the square root there. And you see here that we do end up with a little bit different function, and the position, if you would graph these, they do end up in different positions. So the question, does the order of the transformations matter? Sometimes it does, sometimes it doesn't. It's always best, though, to assume that it's going to matter and follow the order of operations. In other words, take care of things that are in your grouping symbol first, then exponents, multiplication and division, addition and subtraction types of operations in that order. And then you'll be sure that you're not going to have any issues. In this example, we're going to write this equation with a described transformation. Now this is a function that's already had a transformation. It's not just the plain parent function that we started with. So we're going to take this function and reflect it across the x-axis. Now, if we're reflecting something across the x-axis, we want all the y's that we had before to be the opposite of what they are now. So we're taking this f of x function and taking the opposite of all of it. Okay, so f of x is now the opposite of what it used to be. All the y's are the opposite of what they used to be. And so when we simplify this, we will have negative square root of x minus 1. Now, if we have this function f of x equals x squared minus x, and we want to reflect this across the y-axis, then we're replacing the x's with negative x's. So f of x is now going to be this negative x squared minus negative x. So our new f of x is positive x squared plus x, and that reflects it across the y-axis for us. Using transformation, sketch the appropriate parent graph, and the graph of f of x equals 1/2 times the absolute value of x minus 2 minus 3. So let's talk about the appropriate parent graph. The parent graph is going to be y equals absolute value of x, and we can graph that real quickly. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4, negative 5, 5, and so on. So we have this nice absolute value function graphed here. And what are the transformations that are going on? Well, in the order that they occur, this negative 2 that's inside the grouping symbol, remember we do grouping symbols first. This is shifting our graph right 2 units. And then this is the second thing that's happening. That's our multiplying. So that's our next in our order of operations. This means we're going to be half as tall, if you want to think about that way, half as tall as the parent graph, and then minus 3 means we're going to go down 3 units. So now in graphing the transformation, we can pick up, let's say we start with our corner point. We're going to take that and move it 2 places to the right. And it's half as tall. Well, if it's already 0 tall, then it's still 0 tall. Half of 0 is 0. And then we'll move it down 3 units. So 1, 2, 3. So this is our corner. Just write that in there to kind of give yourself a reference. And then let's say we come out here to maybe 4, 4. Looking at this point 4, 4. All right, so our transformation says that we're going to move that right 2 units, and then it's going to be half as tall. So instead of being here at a height of 4, we're going to be at a height of 2. And then we're moving that point down 3 units. So 1, 2, 3. And this is the one part of our absolute value graph. And let's try and get the left side of this. Let's say if we would go over to the point negative 2, 2. So our transformation says we're going to take that point and move it to the right 2 units. So here we are. And then we're half as tall. So instead of having a height of 2, we're going to have a height of 1. Then we're going to take that point and move it down 3 units. 1, 2, 3. And where you land is where your graph goes. So we have a absolute value graph that has been moved right 2 units. It's compressed by a factor of 1/2 and moved down 3 units. Here, using transformation, let's sketch the appropriate parent graph, and the graph of f of x equals negative square root of x minus 3 minus 2. The parent graph is going to be y equals the square root of x. And we can quickly sketch this. These days we're getting pretty quick at sketching those parent functions. Now the graph of f of x has some transformations going on, and that would be first in the grouping symbol. We've moved this graph right 3 units, and then this negative out front says that we're going to reflect our graph over the x-axis, and then the minus 2 says that we're going to shift each of those points down 2 units. So let's pick these points up and use those transformations one by one in order. Let's say we start with our beginning point, and we're going to move that right 3 units. So 1, 2, 3. Then we're reflecting that over the x-axis. Just think, if we folded this on the x-axis, where would it land? Well, it lands right where it is. And then we're taking that and we're going to move it down 2 units. So 1, 2, and that's where we land. And that's the beginning of the graph. Let's say that we start with this point now. 1, 1. We're going to take that and go right 3 units. So 1, 2, 3. Then we're going to reflect that over the x-axis. So we reflect that over the x-axis. We would end up down here. And then we're going to shift that down 2 units. So down here and down here. Next, let's take this point. We're going to take it right 3 units. So 1, 2, 3. Then we're reflecting it over the x-axis. That means we'll end up down here. And then shift down 2 units. 1, 2. Try one more time. We're going to go off grid a little bit here. We're going to take this point and move it right 3 units. So 1, 2, 3. We're going to reflect over the x-axis, so we'll be down here, and then shift that down 2 units, so we wind up there. And we graph this. This is our beginning point, and we're going in this direction to positive infinity. As x goes to positive infinity, we're getting a graph like this. This next example, we're going to look at doing this without a graph, but just explain the transformations that take place in order to obtain the graph of f of x equals negative of x minus 5 cubed minus 4. And remember, we have to put these in the correct order. So the first transformation is inside those parentheses there. When we have x minus 5, it means that we are going to shift right 5 units. Okay. And then multiplication by this negative sign right here. So that means we're going to take this and reflect it over the x-axis. Okay. And then this -4 means another shift. We're going to shift this down 4 units. And so this is your f of x equals x cubed graph with these transformations applied.